Hi, my name is Jim Rautio. I'm going to talk about parameterization of a simple antenna. First, for illustration, I'm going to show you how large of an antenna we can actually do in Sonnet. Then I'm going to load a very simple antenna, a dipole antenna, into Sonnet. We'll explore how an antenna is set up in Sonnet so that you can properly include radiation. Then we'll parameterize the length of the dipole, analyze a range of lengths, and view the results. This is based on a dipole from Chapter 1 of Introduction to Antenna Analysis Using EM Simulators from Artech House, written by myself, James Rautio, and by my close friends for many years, Hiroaki Kogura and Yoshie Kogura. First, how big can we go? Just to see how big of an antenna we can do, I took a 100-turn spiral antenna, 40 centimeters across, on a 1 meter square substrate. This antenna is done extremely fine resolution, 200 micron resolution. The antenna uses 50,000 subsections consisting of over 7 million cells. I'm going to show a detail on the next slide of this very tiny region in the upper right hand corner of the antenna to show you just what a 200 micron resolution allows us to analyze. The big thing that very fine 200 micron resolution allows for this antenna is that we can include edge meshing. Red is high current, blue is low current. We can see we have very high current on the edge of the line. Now remember, loss, I squared R loss, happens where the I is, where the current is. We have high current on the edges, so there's very high loss on the edges. And in fact, edge meshing is absolutely critical for the proper calculation of radiation efficiency. If you don't have edge meshing, you will not calculate radiation efficiency correctly. The 200 micron resolution on a 1 meter square substrate allows us to include the edge meshing, including the effect of the high edge current flipping from one side of the line to the other side of the line. It flips back and forth as you go around the turns. And this again is critical for properly modeling radiation efficiency. With the combination of a 1 meter square substrate and 200 micron resolution and a 100 turn spiral inductor with edge meshing, I think we can say no other EM analysis can do this degree of complexity. For our example, we'll load in an antenna file. First, we'll bring up Sonnet. I'll show you how in a second. Then we'll click on Project from the taskbar. The Sonnet taskbar, we'll click on Project, and then Edit, and then we'll browse for the project, and we'll bring up this antenna. So I'll take down the PowerPoint slides for a second. We'll find the Sonnet icon, double click on the Sonnet icon, and go Project, Edit, Browse for Project. We'll go to the computer. This is the DVD that comes with the book. You can install Sonnet Lite directly from the DVD, and this example can be done on Sonnet Lite if you like. We'll go to Chapter 1. In Chapter 1, we have the dipole. The file is read-only. Of course, read-only to a DVD, so we'll have to save our own private copy of the file. So we'll do File, Save As, find a temp directory. I have one on my desktop. And we'll save the file in the temp directory. Now this is our own private copy, and we can make changes as we like. Summarizing, we brought up the Sonnet taskbar. We did Project, Edit, Browse for Project. We brought up the project, and we saved our own private copy so that we can make changes. Now that's a 1 meter square substrate, and the antenna looks kind of tiny in the middle of it. So we'll zoom on the dipole so we can see mostly the dipole on our computer screen. Going back to the antenna project right here. Going back to the antenna project, we'll pick the zoom key and window out the section that we want. There's our antenna zoomed so we can see it in more detail. You can also use the roller button on your mouse to zoom in and out as desired. Going back to the slides, note that we need a large distance between the antenna and the box sidewall. The box sidewall is at the edge of the 1 meter square substrate. The box sidewalls are conducting. We don't want the conducting box sidewalls close to the antenna. And it's no problem having a large substrate around the antenna for analysis speed. Let's check out the size of the substrate, or actually the size of the box that contains the substrate and the antenna. In the Sonnet project editor, go to Circuit, Box, and we see in the form that comes up, the cell size is 2 millimeters by 2 millimeters. The units are down here. The box size is 1 meter by 1 meter, a little more than that. And 512 cells by 512 cells. 2 millimeter cell size along a 1024 millimeter box edge, substrate edge, gives us 512 cells along that edge. And we have an X-directed edge and a Y-directed edge. It's nice to have a power of 2, slight speed advantage, but it's not required. 500 cells by 500 cells would be just fine as well. The important thing for antenna analysis is note over here on the right, the top cover metal is actually free space. Radiation is allowed from the top cover and also from the bottom cover. So the dipole can radiate in free space in both upwards and downwards, and the box sidewalls are a considerable distance from the antenna, allowing this to model a dipole in free space. Let's go ahead and actually look at the box. Remember, circuit, box, there's the menu, 2 millimeters by 2 millimeters for the cell size. The box size, the size of the substrate, is little over 1 meter by 1 meter, giving us 512 cells by 512 cells. The top cover is free space. The bottom cover is also free space. Back to the slides. Let's check the substrate stack up. To do that, we'll do circuit. Before we did box, this time we'll do dielectric layers. When we go into dielectric layers, we'll see we have two, quote, substrates, 200 millimeters thick, dielectric constant of 1. These are air. We've got air, 200 millimeters of air above the antenna. The antenna is on level 0. The box cover, top cover, which is free space, is at 200 millimeters above the dipole. The bottom cover, on the bottom of the lower substrate, in the lower layer of air, is 200 millimeters below the dipole. This puts the top and bottom covers more than 1/2 wavelength away from the antenna. This is important because we don't want the top covers or the bottom cover to be involved in the near field of the antenna, the fringing evanescent fields around the antenna. We want the box covers to be in the far field of the antenna. Let's go ahead and take a look at that. Circuit, dielectric layers, 200 millimeters of air above the antenna on level 0, 200 millimeters of air below the antenna. Back to the slides. Now we'll show how to parameterize the length of the dipole. We want to vary the length of the dipole automatically so that we can find the desired length so that we get the desired resonant frequency. To set up a parameter, we go to Tools. From Tools, we select Add Dimension Parameter. We will add a symmetric parameter. The symmetric parameter will increase the length of the dipole symmetrically about the center of the dipole, as I'll show in a second here. After we select a symmetric dimension parameter, the cursor will change, and we'll have a cursor note here. It says, click mouse to specify first reference point. The value of the parameter will be the distance between two reference points. Right now we're going to input the first reference point. Later, we'll input the second reference point. So we'll click on, we want the one reference point at one end of the dipole and the other reference point at the other end of the dipole. So we'll put the first reference point right here at the left end of the dipole. On that corner, there's two corners here at the end of the dipole. We'll pick the lower corner on the left end of the dipole. So click the mouse on the lower corner of the left end of the dipole to specify the first reference point. After you specify the first reference point, the cursor will change. The cursor note will change. It says select more points to be adjusted, then press enter to finish. Whenever we move the first reference point as we change the parameter value, we'll also want to move the other corner on that end of the dipole. In this case, there's only one additional point that we want to move when we change the reference point. So click on that point, it will become a dark square, and then since we're finished with there are no additional points, we'll press enter to finish. After you press enter to finish for the first reference point, then the cursor note changes to say click mouse to specify the second reference point. The second reference point will be the other end of the dipole. The value of the parameter will be the distance from the first reference point to the second reference point. So click on the lower corner on the right end of the dipole, and we'll have the second reference point. After you do that, we'll select more points to be adjusted. The only other point we need to be adjusted, when the second reference point is moved, we want the other corner on that end of the dipole to move as well. So select that point as well, and then press enter to finish. Let's go ahead and give that a try. Okay, do you remember? Tools, add dimension parameter, add symmetric. We're going to add a symmetric dimension parameter. Notice the cursor note. Click mouse to specify first reference point. We'll make it right there, the bottom corner on the left end of the dipole. Now select more points to be adjusted. We only want to move, when the first reference point moves, we only want to move the other corner on the left end of the dipole. There we go. That's all the points. Those 2 points will move together. Now press enter. We're all done with the first group. Press enter. Click mouse to specify second reference point. The right end of the dipole, lower corner. And now select more points to be adjusted. Whenever the second reference point moves, we want these points to move as well. The upper corner on the right end of the dipole. We'll select that and press enter to finish. Now we can type in the name of the parameter. We'll call it length. The nominal value, which is what it is right now, is 252 millimeters. Okay. Now we can position the parameter label, the dimension label, wherever it's convenient. and length equals 252. You can change that now. See what happens. Double click on it. Double click, and we'll change it to, let's say, 200. Change it to 200. And see, the dipole is now 200 millimeters long. Let's change it back to 252. 252 millimeters. There we go. The parameter is now set. Back to the slides. Summarizing what we did at the end there. We typed in after we finished specifying both groups of points, we typed in the name for the parameter, length, and then we positioned the label in a desired location. Let's do an analysis now. Now we have to tell it what lengths to analyze. So back in Sonnet, go to Analysis, Setup. After we do Analysis Setup, the menu on the right appears. The analysis control must be changed to Parameter Sweep, and then we click on Add. After we click on Add, the following menu on the left appears. We'll want to sweep length. We only have one parameter here, and it's length. We're going to sweep length, so check the checkbox. We'll start at 240 millimeters, go up to 252 millimeters long, with a step of 2 millimeters. After you're done, click OK, and back in the Analysis Setup menu, it tells us that we're going to analyze from 500 to 700 megahertz, and we're going to sweep the length from 240 millimeters up to 252 millimeters in steps of 2. Let's actually go ahead and do that. Analysis, Setup. We'll change to Parameter Sweep. We'll add a parameter sweep. We're going to sweep the length from 240 millimeters to 252 millimeters with a step of 2 millimeters. And that's exactly what we're going to do. The next step, we click Analyze. This icon, the next to last one, is Analyze. Of course, the project needs to be saved before we actually do the analysis. We'll delete the previous results, which were already there. And now we're analyzing. 0.75 seconds, 3/4 of a second per frequency. 2 cases are already complete. Now it's completed 3 cases. It's working on a 4th. If you count, it's actually analyzing 4 frequencies adaptively chosen, and the results are very intelligently interpolated between those 4 frequencies to provide the entire dipole response from 500 to 700 megahertz. It's all done now. Let's plot the result. Here's the result. Wait a minute. There's only one curve. We did 7 cases. Where are the other 6 curves? That's easy. Come over here to the legend, dbs11. Double click on dbs11. Down here, let's move it up a little bit. It says graph all combinations. There are the other 6 cases. Okay. Now we have the 7 cases. It started out, the longest dipole is resonant a little bit below 560 megahertz. Let's say we wanted the dipole to be resonant at 580. This curve right here is resonant at 580, and that curve corresponds to a length of 242 millimeters. That will be our dipole design. Returning to the slides, summarizing what we just did. We click on Analysis, the analysis icon. The analysis proceeded, just a few seconds. And then we clicked on the View Response icon. We got a plot of one curve. Double click on the S11 label in the legend, and then click on Graph All Combinations. All the other 6 cases show up. Click on OK, and there are all the cases. You select the response that you want, read off the value of the parameter, and your design is done. In conclusion, yes indeed, Sonnet can analyze antennas. I've taken an example from new book, Introduction to Antenna Analysis Using EM Simulators, written by myself and my dear friends Hiroaki Kogura and Yoshie Kogura in Japan. The antenna length is parameterized, and a parametric analysis sweep is performed. Thank you for your kind attention.